In today's video, we'll talk about inelastic collisions. Inelastic collisions are collisions in which momentum is conserved but kinetic energy is lost. So, since kinetic energy is lost, the energy must be converted into other types of energy, such as heat, sound, or work. Inelastic collisions can be perfectly inelastic, meaning that momentum is conserved, the kinetic energy is still lost, but the two objects stick together after the collision, so that their final velocities are the same. And this can be expressed with the equation below. And we can see to the right there's a few examples of some perfectly inelastic collisions. In our first example, we see a freight train has two boxcars, where boxcar 1 has a mass of 65 times 10 to the third kilograms and moves at a velocity of 4 meters per second. Car 2 has a mass of 92 times 10 to the third kilograms and a velocity of 2 meters per second. If boxcar 2 collides and couples with boxcar 1 and we neglect friction, find the final velocity of the boxcars after they become coupled. If we summarize the information that we're giving, the mass of boxcar 1 is equal to 65 times 10 to the third kilograms, and the mass of boxcar 2 is equal to 92 times 10 to the third kilogram, with the initial velocity of boxcar 1 being 4 meters per second and the initial velocity of boxcar 2 is equal to 2 meters per second. And since the boxcars couple at the end, we'll only have one final velocity, which is unknown. If we apply the conservation of momentum equation, we'll get the mass of boxcar 1 times its initial velocity plus the mass of boxcar 2 times its initial velocity. And since this example is a perfectly inelastic equation, it will be equal to the mass of boxcar 1 plus the mass of boxcar 2 times the final velocity of the coupled boxcars. So since we're trying to solve for the final velocity of the boxcar, we can rewrite the equation where our final velocity is equal to, if we solve for the final velocity of the coupled boxcars, we can plug in the values we're given. The mass of boxcar 1 is 65 times 10 to the third kilograms, multiplied by its initial velocity of 4 meters per second, plus the mass of the boxcar 2, which was 95 times 10 to the third kilograms, times its initial velocity of 2 meters per second, all over the mass of boxcar 1 plus the mass of boxcar 2. We see that the final velocity of the paired boxcars will be 2.83 meters per second. In our second example, we see that we have two blocks that move with the given velocities. When they collide, they stick and move together. Find the velocity of the blocks after they collide. If we summarize the information we're given, we see that the mass of block 1 is 3 kilograms and has an initial velocity of 4 meters per second, while the mass of block 2 has a mass of 4 kilograms and an initial velocity of 4 meters per second. Since block 1 travels in the x component and block 2 travels in the y component, we can apply the conservation of momentum in the x direction and in the y direction. So the sum of our momentum in the x direction will be equal to our mass of block 1 times its initial velocity plus the mass of block 2 times its initial velocity is equal to the sum of block 1 plus the sum of block 2. Since this is a perfectly inelastic collision, the masses are coupled times their final velocity. So if we plug in the values we're given, the mass of block 1 is 3 kilograms times its velocity of 4 meters per second plus the mass of block 2 and its initial velocity. However, since we're looking at the x component, we see that block 2 velocity is only directed in the y component. So the velocity in the x component will be equal to 0, therefore making this part of the equation equal to 0, which is equal to the mass of block 1 plus the mass of block 2 times its final velocity. And then the same can be done in the y component. We can take the sum of the momentum in the y component, which will be the mass of block 1 times its initial velocity plus the mass of block 2 times its initial velocity equal to the sum of our masses times our final velocity. And in this case, we see that the initial velocity for block 1 in the y direction is 0, since block 1 only has a velocity acting in the x direction. We see that this part of the equation will be equal to 0 plus the mass of block 2 is 4 kilograms and times its velocity acting in the y direction of 4 meters per second is equal to the sum of our masses times our final velocity. So you might recognize that from our x component, we have the sum of the momentum in the x direction, the sum of the momentum in the y direction. We can use Pythagorean's theorem to solve for the hypotenuse of this right triangle. If we do so, we see that our final momentum will be equal to the square root of our momentum in the x direction squared plus our momentum in the y direction squared. We can plug in our values. See that our momentum in the x direction will be 3 times 4, which is 12, squared, plus the momentum in the y direction, which is 4 times 4, which will give us a value of 16, squared. And when we take the square root, we see that our momentum is equal to 20 kilograms times meters per second. And since we know that momentum is equal to mass times velocity, we can apply this to the information we're given. We know that our momentum is 20 kilograms times meters per second, and our mass is the sum of our two blocks, which was 3 kilograms plus 4 kilograms, is equal to our final velocity. So now we can rearrange this equation and solve for our final velocity. When we do so, we'll have our final velocity is equal to our momentum divided by the sum of our two masses, which when we add them together, we'll get a total mass of 7 kilograms. And when we divide this out, we'll see that our final velocity will be equal to 2.86 meters per second.